Okay, today we're going to be looking at whether or not a galvanic cell runs spontaneously. So we're going to be asking the question, is a cell spontaneous? And you might remember asking that in Chapter 17 on spontaneity. We know that a reaction is spontaneous when delta G is less than or equal to 0, meaning it has to be negative. All right? So we're going to do this with an equation that's going to translate cell potential into delta G. It looks like this. Where obviously this guy, this E here is our cell potential. So if we know this is cell potential, this guy N is going to be the number of moles of electrons transferred in the cell reaction. This guy F, this is a unit of charge per mole of electrons. It's called a Faraday. And it has a pretty interesting unit. 1 Faraday is equal to 96,485 coulombs per mole of electrons. Now, if you've never had a physics class, you've never heard this term before. Coulombs is simply a unit of charge. And so another way of describing voltage is how many joules of work are done to transfer 1 coulomb of charge, because you know that like charges repel. So if you're going to stack a bunch of electrons, like say in a battery, you know that that requires work. Take a good physics class and you'll get to that. We're not going to worry about that so much. So what we want to know is how many moles of electrons are being transferred, the amount of charge for each mole of electrons, and how much work is done to stack those. You'll see how it works as we go, okay? So let's take an example here. So we have this reaction. We're going to calculate delta G and determine if it is spontaneous. So we're going to need to know a couple of things. 1, what's the voltage? And we can find that by finding the cell potential. So we also want to find out how many moles of electrons are transferred. So let's do 1 first. Let's find our 2 half reactions here. So we know that in this reaction, copper is going from 2+ to copper with a charge of 0. And that means that we have to have added 2 electrons. And that means that this is our reduction. And that means that this has to be the cathode, because this is where the electrons are going. Our other half reaction, we have iron, which is solid, and that means has a charge of 0, and it is being oxidized to Fe2+, and that means that it is getting rid of 2 electrons. And that means that this is oxidized or oxidation, and which means this has to be the anode because this is the source of electrons. Okay, so let's line these up and find out what our potentials are. So this is our reduction. Let's write it in the order of a reduction so it looks more like our half reaction. So U2 plus 2E yields copper with a charge, with an oxidation number of 0. We're going to find that here, and this one is right here. Has a potential of 0.34 volts. So here, 0.34 volts, and this is the cathode. The other one is iron that is oxidizing. It is losing 2 electrons. And if we look in our cell potential table, we want iron with 2 electrons, and it can be tricky to find because there's lots of different versions. And I should have looked for this before I started this video, but that's part of the fun. Let's be careful because this is negative 0.44 volts. So we'll put that right here. Okay, remember that when we are doing this and we are trying to find subpotential, it's equal to the potential of the cathode minus the potential of the anode. And remember that when we're doing this, all we're doing is reversing the sign of the anode and then add. Okay? So in other words, if we were going to do this, our subpotential, you could look at it a couple ways. For you math geeks, we're going to say 0.34 volts is our cathode minus negative 0.44 volts, or since we're just reversing the sign, 0.34 volts, and we're just adding 0.44 volts. So let's do that. Here is my flashy calculator. If you're interested on how I got this, I'll be happy to show you, although it's kind of tricky. But it's pretty neat, so you don't have to lug around a TI-84 all the time. So we're going to say 0.34 volts time, plus 0.44 volts. We have a cell potential of 0.78 volts. Okay. Now, we're going to plug this into our equation for delta G. It's equal to negative NFE, and we just found E. What we want to be looking at is how many moles of electrons got transferred. And what's nice about this one is that there's 2 moles of electrons being transferred in both sides. Now, if this is one of those reactions where you had to balance charge, you would multiply by the final mole. So if this one was, say, one of these had 2 electrons and it had 3, you'd multiply them both to get, we'd multiply 2 by 3 and 3 by 2 to get 6, and then our moles would be 6. This one's a little simpler, so we're not so worried about it. So let's find delta G, and we're going to write our units a little differently. So we know we have negative 2 moles of electrons times a Faraday, which is 96,485 coulombs per mole of electrons, times our voltage. And we're going to write this a little differently. Okay? We're going to say that we have 0.78 volts, which, if you will recall, we wrote a little differently. Joules per coulomb. When you do this, look at what happens to our units. Moles of electrons cancel, coulombs cancel, leaves our answer in joules. So let's bust this out and see what we get. We know our answer is going to be in joules. We hope that this is a negative cell potential. It should be because everything else is positive. So let's bust out a calculator, and we're going to say negative 2 moles of electrons times 96,485, which is our Faraday value, times 0.78, and we get negative 150,516.6. Let's convert that to kilojoules by dividing by 1,000, and we'll round up. So negative 150.5, let's call that negative 151 joules. And that's all we do.